Hello, algebra friends, and welcome to our new chapter. This is chapter 3, which we learn all about polynomial functions, how important they are, what we could use them in real life for, but a really, really cool chapter overall. And in this first section, we focus on our friend, the quadratic function. Now, we learned a little bit about the quadratic function in chapter 2, about shape and about the equation, but we're going to dive really deep into it in this chapter. So first of all, can we define polynomial? Poly means many. And you see nomial, which sort of means many names. And that's really, really similar to what a polynomial is. Basically, our functions that are polynomials have many terms. Many, many terms. Look at some examples down here. For example, I have 1, 2, 3, 4, many terms. Or even just 3. But it's a function that has many, many terms. And that's a polynomial. So, for example, f of x is x to the 5th minus 4x to the 4th plus 2x squared plus 1 is a good example of a polynomial. And so is g of x over here, minus 4x cubed minus 2x plus 9. They are functions that have many terms. And the way we're going to describe them and classify them is by whatever their highest exponent is. For example, over here, f of x, the highest power exponent is a 5. And then g of x, the highest exponent over here, is the 3. So we're going to call that, if you remember, the word degree. So the degree of f of x is 5. And the degree of g of x is 3 because that's the highest exponent. Now quadratics, if you remember, quadratic was some version of y or f of x equals x squared. So your degree for all quadratics will always be a 2 because the highest power will always be x squared. They kind of appear in different forms. You can have, for example, this quadratic here. Again, you can see the highest power is 2, so it is a quadratic. And we have h of x over here is another version of a quadratic. It's a little bit hard to tell that it is, but if you can imagine, if we actually FOILed this out, our highest term would be some version of x squared. So that's also a type of quadratic. And we'll play interchangeably with both of these two forms, and they each have their own name. But let's focus on the one left for a second. This one is one that's a little bit more popular that you probably saw a lot in Algebra 1. This was called the standard form. Standard form of quadratic is basically with these a's and b's and c's. Take a look at this formula. F of x equals ax squared plus bx plus c, where a, b, and c are just real numbers. They could be positive, they could be negative, they could be zeros, they can even be square roots, but they're all real numbers, nothing imaginary. So that's one form that we have of a quadratic. The other one's going to look like the one over here on the right-hand side, but we'll get to that a little bit later. But can we talk about the shape? Okay, what did these things look like when we graphed them? And in chapter 2, we knew they made this cool little sort of U shape. But do you know what we call that shape? That's called a parabola. So whenever you graph a quadratic, it's always in the shape of a parabola. Linear is always a line, and quadratics are always in the shape of a parabola. Now, depending on how your equation looks, your graph is going to be either facing up or down. For example, I could have one that opens up like this. There's a good example of a parabola, which is from a quadratic. Now it opens up because if you're given ax squared plus bx plus c, the front number, the a in front of the x squared, is positive. And if a is positive, he opens up. We're very happy about that. We're positive, so he opens up. The cool thing about parabolas, too, if you noticed, is they are kind of symmetric. I could actually draw a line right here that would cut it in half, and I could sort of fold one side onto the other. Well, that dashed line is called the axis of symmetry, and all parabolas have it, and it goes right through the middle. And in fact, not only does it go right through the middle, it actually goes through a very, very special point here. Right there, it's the lowest point, which here is called the vertex. The vertex of a parabola is the lowest or highest point, but also is the point that crosses through the axis of symmetry. All right, so there's one example of a parabola. That's one that opens up. But what if by chance you have a parabola where the a value in front of the x squared is negative? If that happens, he's going to open down like this. So if your a value is negative, he opens down. Okay, but you know what? You still have the axis of symmetry that still cuts this parabola in half. And not only that, we do have a vertex here. It's the point where the axis crosses through the parabola. But notice here, because it opens down, My vertex is the highest point. It's the maximum. When it was opening up over here, it was the lowest or the minimum. And when it opens down, the vertex is the highest or maximum. But the vertex is always the point where the line of symmetry, axis of symmetry, crosses the parabola. So how can we graph these by hand really quickly? Well, first of all, we need to learn a little bit more about the vertex. So let me show you a little shortcut. How can we find the vertex of a parabola if I give you the equation really quickly? Okay, if you have y equals ax squared plus bx plus c, our standard form, we're going to take the b and we're going to take the a values, and here's your magic formula. Ready? Write this down and put a big star next to it. To find the x-coordinate of your vertex point on your parabola, the value will always be negative b over 2 times a. Okay, negative b divided by 2a. Memorize that. And that will give you, on your vertex, the x value right there. Now, how do you find the y value for the vertex? Well, you're just going to take that x value that you just got, and you're just going to plug it back into the original standard form equation and solve for y. So x-coordinate would be negative b over 2a, and the y-coordinate would be by taking your x-coordinate that you find and plugging it back into the original function. Okay, but remember, on these graphs, when you have a parabola and you have a vertex, remember that the vertex is always the point that crosses also through the line of symmetry. So if you think about it, if this is my vertex here, some x, comma, y, do you believe that the value of this vertical line will be x equals the same x value of the vertex, right? Because it's passing through the same x value of your vertex. So if you want to find the equation for the axis of symmetry, the line, the vertical line that goes through it, it is going to be the same negative b over 2a. So no matter what, you can always take our standard form and either find the x-coordinate of the vertex, negative b over 2a, or you can find the line of symmetry equation, negative b over 2a, because they pass through the same value. Shall we play? Let's actually try it. Okay, you've memorized negative b over 2a. Let's do it. All right, I want to graph this equation here without a calculator. Let's do it by hand, of 2x squared minus 8x plus 6. I see that my degree is 2, so I know it's going to be a quadratic. So it's going to be a parabola that either opens up or opens down. But hey, can we figure it out right now? Does it open up or does it open down? Remember that we look at the a value here, and the a value is 2, which is greater than 0. So that means it's going to definitely open up. Great. And that's going to also mean that the vertex is going to be the lowest point or the minimum. So let's actually find that vertex. Shall we do it? All right, our magic formula for the vertex is negative b over 2a. And let's look at our equation here. Where is a, b, and c? Let's see. The 2 here I think is the a. The negative 8, the entire with the negative, is also the b. And the positive 6 is going to be the c. So negative b over 2a should be negative, b is a negative 8, over 2 times your a value, which was the 2 in the front. This becomes a positive 8 on top, 4 on the bottom, which is 2. So I know that my vertex is at 2 comma something. And we need to find that something. The best way to do that is let's just go and plug our 2 back in for x and see what the y value is. Okay, why don't we do that over here on the left-hand side? So what is y when x equals, let's see, 2. Let's plug it in. Minus 8 times 2 plus 6. All right, PEMDAS says we got to square that 2 first. So 2 squared is 4 times 2 minus 8 times 2 plus 6. That sounds like about 14 minus 16, or negative 2. So my vertex over here on the right-hand side, friends, is 2 comma negative 2. Good. Look how we used our formula to find that, and then we just plugged in our x value to find the y. Awesome. All right, 2, negative 2. Let's graph it. So I go 2 to the right and 2 down, and there's my vertex. And I'll put v there to label it for myself. Now, because we have the vertex, remember, the vertical axis of symmetry should go right through that line. So why don't we go and just draw a little dashed line that goes through that vertex. And we should label it. What's the equation of that vertical line? Well, it goes through 2, and it's a vertical, so it's always x equals. So x equals 2 is my label. Great. Now, here's a cool thing we can think about. On a parabola, if this is going to open up, and if he's got symmetry, do you folks believe that if I can just find maybe 1 or 2 points over on one side, because of this symmetry line, I'm going to have the same points reflected over on this side. And that should give me enough to draw it. So really all I have to do is just find 1, 2 points on one side of the axis, either on the left side or on the right side, and they should naturally reflect over. So why don't we make sort of a mini XY chart over here? And let's pick a couple values, maybe to the left of x equals 2. Well, let's see, a couple of values over here would be maybe x equals 1 is good. And x equals 0 is always really nice to plug in. Cool. So 2 really easy points to plug in to the left of my axis of symmetry. Now, the y values, why don't we go and plug them back all the way back up here where my equation is. If I plug in 1, go and do some quick math, and you'll see that I'll get 1, 0. Great. Now, that gives me a bonus point, right? That gives me a bonus point at, let's see, 1 to the left of the axis means 1 to the right, which would be 3, 0. Wow, that was easy. 2 points for 1. Now let's plug in 0. All right, when we plug 0 back into your original, a lot of the x's die, and you're just left with 6. So I'll graph that point up here. And if that's 2 to the left of the axis, then 2 to the right of the axis should be here at the same reflected point. And that's about 4, 6. There you go. So we really only need to graph 1, 2 points, and as a bonus, they gave us these 2 reflected points on the other side. And you could have started on the right side first if you wanted to, and then reflected to the left. Either is fine. All right, should we graph it? Here we go. And we connect the dots. We know it's going to open upwards and give this great little curve. And we did it. So step 1, we found and graphed the vertex using our negative b over 2a. We drew our axis of symmetry and we labeled it x equals 2 down here. We picked 2 points on one side and we graphed them using XY chart. They reflected over to the other side using our axis of symmetry. And then we just basically connected the dots. And that's how you can graph a very basic quadratic in standard form. Good. Now, what about x-intercepts? X-intercepts, as you see, is where it intercepts the x-axis. So it's here and here. I can see that. So I can see that it's probably at, let's see, 1, 0 and 3, 0. Or at x equals 1 and 3. Is there a way I could have done that without the graph, though? Is there a way I could look at my original equation, y equals 2x squared minus 8x plus 6? Is there a way I can find the x-intercepts there? Do you folks remember from Algebra 1 days? The x-intercept is where you cross the x-axis, which means that's where y is always 0, right? Everywhere along this axis here, on your x-axis, y is always a value of 0. So what we can do is just set 0 equal to y here and try to solve. So I'm going to try that. Let's say 2x squared minus 8x plus 6 equals 0. Oh, okay, well he's a quadratic, so the clue here is we usually try to factor, just like we did in the beginning of the year in Chapter P. All right, well, the best thing to do to factor this is maybe look for a good GCF. I see there's a 2 in everything, so I'll factor out a 2. Great. And then I see those parentheses do factor very nicely. How about x minus 1 and x minus 3? Great. Beautifully factored. If you remember, folks, once you factor, that means every one of these factors equals 0, and we'll solve each one and see what x gives us. From the first one on the right, where does x minus 3 equal 0? That's where x equals 3. Great. On the middle one, where does x minus 1 equal 0? Well, when x equals 1. Great. And lastly, the number in the front, it's important to look at, where does 2 ever equal 0? And does it? And it doesn't. So we can just ignore the 2 in the front. We're only going to worry about the pieces that have x's in them. Well, look what you found, friends. You found x equals 3 and x equals 1. Oops. Which is exactly what we found visually. So if we ever need to find it algebraically before we graph it, we can just take the equation, set it equal to 0, and then do some factoring. All right, folks, why don't you try number 2 on your own? Can you graph this quadratic in standard form? Remember to label your vertex and your axis of symmetry. Go, and if you want to find the x-intercepts as well, and we'll see how you do. I'll pause the video, and we'll join up in just a second. Good luck. All right, friends, let me show you what I've got so far and see if we match up okay. I did negative b over 2a to find the vertex. I did that over here. We've got some pretty big numbers over here, but it's not too bad. We can do it. And my vertex ended up being negative 4 for the x value. I plugged it into the y, and I got 8. So negative 4, 8, I'm going to put up on my clean graph up here, and I label it with a v. And I'm just checking to see. That's pretty high up there, but I'm okay because you see how the a value here is negative, so I know it's going to open down. It's going to be a downward parabola, so that makes sense. Okay, sounds good. So now we're going to check and see. Let's draw our axis of symmetry, and we'll label it. And that is x equals, well, what was the negative b over 2a? It was negative 4. So x equals negative 4, the same value. Great, and then I started picking some values over here to this time I picked the right-hand side because they ended up being a little bit smaller over on this side versus on this side. So I'm just going to plug in some smaller numbers. When I did it, I got negative 3 gave me 6, which reflects over and gives me over here. That would be, see, if it was 1 away from the axis of symmetry, that would be negative 5, 6. And when I got negative 2, I got 0. And that was 2 away, so if I take 2 away to the left-hand side, I get negative 6, 0. And they reflect right over. I think we're ready to connect the dots. Shall we do it? Here we go. Very steep one. Okay, there it is. Great. So that's how my graph turned out to be. That's a downward one with my axis of symmetry at x equals negative 4. Shall we try x-intercepts? Let's see. Let me make a little bit of space here. Let's do this by setting the whole equation equal to 0, because that's when y equals 0 as the x-intercept. So basically right here, set equal to 0. Factoring, let's take out a negative 2. I get x squared plus 8x plus 12. And that does factor more on the inside. How about x plus 6? X plus 2. If we solve each piece, again, we could ignore the negative 2 on the outside, but this piece here would give me x equals negative 6, and over here, the second parenthesis would give me negative 2. And that matches my graph, and it actually matches my chart, too. Great, so my x-intercepts are at x equals negative 2 and negative 6, and that's my graph. Great job, folks. How did that first one go? Awesome. So that's one form that we can draw it in. The next one we can actually try looks a little bit more like this, and it's called vertex form. So we now know standard form. Great. Y equals ax squared plus bx plus c. But another form to try it in would be this here. This is very similar, if you remember from the front page, right over here. So we did this one, and now we're going to focus more on when you look like that. That's a really interesting one. That's called vertex form, and the reason why, do you see the h and the k there? H and k. Those two numbers are, in fact, the vertex. It's really right there staring at you at your face. It's really right there. So you don't have to use negative b over 2a anymore when you are in vertex form. The vertex is right there. And not only that, remember, if this is the x value of the vertex, it's also the same value of your axis. So these are a little bit faster and easier to use because you don't have to go through the hard work of finding the vertex. This is vertex form. So watch out for the h and the k. The only thing to be careful of is according to our formula, this is x minus h, and you take the positive h out. And this is plus k, and you take the plus k out. All right. Shall we try one? For example, if this is y equals 2 parentheses x minus 3 squared minus 5. Now, it doesn't look like standard form. I don't see ax squared plus bx plus c. I do see a parenthesis squared, and that's usually a very good clue that this is in vertex form. Okay, so if this is supposed to be x minus h, your h value would be, well, let's see, it was x minus h. We would take positive 3. And on the outside should be a plus k, so we take exactly what it looks like, and we get minus 5. So in general, I just look at the parentheses and I say, well, I see minus 3. Okay, I'll take the opposite. I'll take a plus 3. On the outside, I take exactly what it says. It says minus 5. I'm putting a minus 5. So there you go. Now, the graph would look exactly the same. We'd still have to plot a couple of extra points here and there, but finding the vertex is so fast. 3, negative 5. Good. Let's try one. Okay, here we go. We see vertex form one more time. Now, it's hard to tell, but the a value in front here is negative. So it is going to open downward. Why don't we figure out what our vertex is? Okay, I see x minus 2, so I take a positive 2, take the opposite. On the outside, you see a positive 3, so 2 comma 3. Great. That was fast. And not only that, I can draw my axis of symmetry. And that's at x equals same x value as the vertex. All right, now let's graph a couple of points over here. Let's take the left-hand side, because again, I see 0 and 1 are really nice to plug in. Now, plug in, just be a little bit careful when you do plug in, folks, because you're plugging into this form now. So you got to start on the inside and start working your way outside. So if I plug in 0, I would get 0 minus 2 squared plus 3. Let's work with the parentheses first. And now I get exponent first. And that's what I have. So 0, negative 1. Gives me another reflected point over here, 2 away at 4, negative 1. Now let's plug in 1. If I plug in 1, I get negative 1 minus 2. A lot of negatives there. Watch your order of operations, and I get 2. So 1 comma 2 is on there. That means reflected over there, I get 3 comma 2. I'll kind of fit into my graph here. 3 comma 2. And there you go. Opens downward. Vertex is a maximum. Looks great. So the fast thing here is just finding the vertex is really, really easy. Trickier thing maybe on this one is just plugging the values in for your XY chart. Just a little bit different. A little bit different. Okay, folks, that's as far as we want to get today. You got a good introduction to polynomials, specifically the quadratics. You see that they're parabolas, and they're really useful in real life things. We're going to talk later about when you can throw things in the air, they're going to always follow a parabola. Why? Because we naturally have gravity. It pulls it back down. So we're going to talk about how can we apply these to real life. But a great, great introduction to quadratic functions, folks, and we'll see you next time.